So we'll start with the introduction to Icepack. I'll take you to the brief what Icepack is, Icepack Classic is, and where it can be used, and what are the capabilities. And I'll give you a brief overview, and then I will take you to a tool, and I'll showcase one demo of the same. So yes, we will start with the basically before starting with the Icepack, we need to understand what CFD is. So basically, Icepack works on CFD. The solver used in Icepack Classic is CFD solver, which is based on Fluent. So what are the Ansys solution for electronic thermal management we will be seeing in the upcoming slides, workflow of Icepack Classic and the multi-physics workflow with Icepack. So what is CFD? So basically, CFD stands for computational fluid dynamics. It is the science of predicting fluid flow, mass transfer, chemical reactions, heat and mass transfer, and the other related phenomena. These are the predictions which are based on the some numerical equations known as the conservation of mass, momentum, and energy equation. So where CFD or let's say ISPEC can be used in which engineering stage it can be used in engineering processes. So basically, you can use the simulation tool, whether it's ISPEC, whether it's let's say CFD, whether it is mechanical or whether it's electronic simulation. You can use these tools at the conceptual studies of the new design when you are designing a new product, or let's say detailed product development where you are particularly developing a pretty much detailed product like whole component. For optimizing, you can use it for troubleshooting. Let's say you have developed one of the components and you are seeing there is a thermal failure, or let's say there is a CPU in which CPU consists of an SMPS box. So let's say your power heat generation in the SMPS box is comparatively high as it should be. So in that case, you are exceeding your maximum thermal limits. So in that case, troubleshooting will help you. You can analyze your uh, product with the help of simulation, virtual simulation. Then for redesigning of any of the products, you can see whether the redesigned product is performing at its best or whether it's matching the required criteria or not. In this way, CFD iSpec can help you. So why does we go for this types of analysis, or why does we tend to move towards the CAE part domain? So basically CFD analysis complements physical testing by reducing the total efforts. Hello.
हमारी कंपनी का है। अच्छा ये तो
Uh,
एलमेक का है ना।
uh,
वो
yes
टूलिंग का
sir.
सप्लायर है। वो सप्लायर टूलिंग के तो अभी नहीं बाद में बनाते हैं। वो टूलिंग के
So
सप्लायर है।
total and cost required for the experimental and data acquisition. So what does this sentence mean? So when you go with any of the CAE tool or domain, let's say you can reduce it by performing the virtual simulation. You can replicate the physical testing into a virtual environment using any of the CAE tools, whether it's mechanical, CFD, or ISPEC. And you can reduce your physical testing. Let's say if you are doing 10 number of iterations in physical test, you can reduce it to 7 or 8 depending upon the application and the accuracy of the CAE results. So you can actually reduce your computational time, you reduce the physical time of testing, and you can save that resources and money as well to develop the prototypes. So moving towards how does the CFD work? So CFD basically works on the governing equation, which is also known as the general transport equation. So this is the basic equation on which the CFD works, which consists of unsteady convection, diffusion, and generation of the terms, which is basically known as X, Y, and Z momentum and continuity and energy equation. This is the combination of partial differential equations. So then we discretize the domain into small elements. So basically, one more thing I would like to add over here is whenever we go with any of the simulation, whether it's ISPEC, whether it's electronics, whether it's mechanical, or whether it's CFD, the simulation process, complete process is done in the 3 steps. So the three steps are pre-processing, solver, and post-processing. So basically, these are the pillars. You have to follow these three steps in order to reach your results. So what comes under pre-processing is when we talk about pre-processing, the CAD cleanup and the meshing part. So we need to remove all the unnecessary elements from our geometry, and we need to keep only the focus and the major components. The components which will not create impact on removal, we will eliminate all those components. Then we will perform the meshing. So what is meshing? So basically on the right hand side, top corner, you can see one diagram is there. A bent tube is there. So here you can see grids are drawn over here, and one small cuboid is over here. So basically this is known as the control ball. When we have long geometry or when we have any geometry, we discretize that geometry into small control volumes. So this is known as meshing. So this is the second step of pre-processing. Then comes the solver part where we give our inputs. Let's say we give our boundary conditions. We tell the software like this is this much inlet of air is going to enter our system, or this much temperature will be there at the initial point when the simulation is going to start. This is the initial conditions. So these are all known as the boundary conditions. So this will come under solver part. Then comes the third part, that is post processing. So pre-processing is done. We have given the inputs to the system, and then the solution will take up place by the computer. The solver will solve all the equations, and it will give us some colorful diagrams, graphs. So all those diagrams and graphs are tend to be done in known as post processing. So where we can visualize the things, we can analyze it with the help of numbers. So these all things will come under post processing. So anyone, if you have any of doubts, you can just ask me, interrupt me and ask. So I'll clear it up. So this is how CFD simulation or Icepack simulation works. So now we will be seeing the solution for electronics thermal management. So basically this is the domain, different modes of heat transfer. So Icepack is known for its thermal management for electronic components. So when we talk about the thermal management, the first thing which will come in our mind is the heat transfer. So there are different mode of heat transfer. As we already know, there is conduction, convection, and radiation. So how does we will get this kind of heat transfer in our simulation tool? Is it available or not? So let's say conduction, convection, and radiation. These are general purpose and included in Ansys Fluent as well as Discovery as well as in Icepack. When we talk about conduction and radiation specifically, so these are also available in Ansys Mechanical, which is structural software. So when you are content, your focus is for the structural analysis, mechanical structure analysis, fatigue analysis, model analysis. At that point of time, Ansys Mechanical is there. In Ansys Mechanical, convection mode of heat transfer is not available. It works on conduction and or radiation. But when it comes to Ansys Icepack, that is specifically designed for the electronics cooling, and as it uses Fluent as the solver, so all the capabilities of Ansys Fluent will be carried to Ansys Icepack, which means you get conduction, convection, and radiation, all the three modes of heat transfer to simulate your problem. Let's say you are having one of the components, let's say CPU. Your CPU is kept in some hotter area, warmer area, not in the regular AC system room. So in that case, if you also want, it is exposed to open atmosphere. In that case, if you want to include the radiation, what are the heat, how the heat is gaining with respect to radiation? Because if there is direct sun rays, it's obvious that the system will get heated up faster as compared to the system which is kept in a cooler environment. So this kind of radiation can also be included while working in Icepack and Fluent. So this is the different versions of Icepack. There is one AEDT Icepack which is based on the uh, electronics device, electronics components part. Similar way, Ansys Icepack Classic is also available, which will be our major focus. Other Icepack is SI waves, and then the last one is classic Icepack. So our focus will be for classic Icepacks. So all we will get the different kind of turbulence flows when it comes to any of the CFD simulation or related to CFD simulation. Turbulence plays an important role. So a number of turbulent models are available, whether it is laminar or it's turbulent. All the models are available both in ADT as well as in classic ISPEC. So these are few of the highlights, like which kind of simulation you can use in which tool. So when it comes towards the ISPEC Classic, you can perform your steady state simulation, your transient analysis. So when we talk about steady state, let's say we perform one simulation, we want to only see the final, what is at the end of the final result. So that is known as the steady state analysis. Now, when we come towards transient analysis, so transient analysis is, let's say you are running your solution for 10 seconds and you want to see whether the initially what happens, how the flow or temperature behaves with one after 1 second, after 2 seconds, after 3 seconds, with respect to time. With respect to time, you want to see how your temperature is rising. That will come under the transient analysis. In similar manner, you are having the comprehensive MCAD and ECAD support. So when we say MCAD, it's a mechanical CAD, and ECAD, it's known as the electronics CAD. So we can import the geometry from SpaceClaim into iSpec Classic. We need to perform certain operations in SpaceClaim to convert the SpaceClaim normal mechanical or fluids files into the iSpec Classic files. Then automated package characterization is available, single or multiple fluids. Whether let's say you are also using the cooling channels to cool down your electronic components. There are multiple ways how we can and simulate or analyze the thermal behavior. And once we know, yes, like our system is heated up pretty much higher, we then design the cooling jackets. We design the thermal path for cooling. So in that case, there might be multiple fluids involved in it. Hello. So there might be multiple fluids involved. So that will come under the multi-phase flows. So multi-phase flows is also supported in Iceplack Classic. So coming towards the advanced modeling, so trace map is there, Joule heating is there, solar load modeling is there, MRF is there, and TEC modeling is there. So when it comes to the trace mapping, all the traces on the PCB board can be mapped. Joule heating. So let's say you are having a PCB board and all your copper tracks are on the board. So you want to see how much rise in temperature is there through that copper tracks, or the XYZ material is there. How your paths and traces are behaving in terms of thermal behavior. So that can be simulated, that can be analyzed through IcePack Classic. Apart from that, you also get solar load modeling. So when we come to solar load modeling, when we use the radiation model, the solar load model gets enabled. So there, in solar load model, we need to enter the latitude and the longitude. The system will automatically calculate the heat flux data, solar load data. We don't have to, if we have the data, we can input it manually. Otherwise, we can calculate it from the solar load model. Then coming towards MRF modeling. So when we model any fan, it's a transient and heavy procedure. So for that, there is a multiple reference frame modeling. So it will give you the results similar as of you have run the transient simulation, but MRF will be based on steady state modeling. Apart from that, parametrics and optimization is there. So when it comes to parametrics and optimization, let's say you want to parameterize the various flow rate of the fan. So here in the top, you are seeing there are two fans, right? So let's say your flow rate is varying. You want to see how your fans are performing, whether the fans flow rate is sufficient to cool down the components or not. So let's say for initially you have given the velocity of, let's say 2 meters per second. Now you want to see like 2 meters per second is higher or lower. So let's say you want to see it by how the thermal performance is there if I use the same fan at 1 meters per second of velocity, and you want to compare it with 3 meters of uh, 3 meters per second. So you can parameterize that inlet velocity condition, and you just have to enter one. Let's say you want to analyze it at 1 meter per second, 2 meter per second, 3 meter per second, 4 meter per second. So you just have to enter that 1, 2, 3, 4 values, and that will automatically give you the conditions, like what will be your behavior based upon which parameter you have selected. Then coming towards optimization, you can always go with the optimization. You can The system will suggest the optimized shape, and then you can go ahead with the simulation further. Then multi-physics coupling is available for electrothermal and thermomechanical analysis for chip, package, board, and system levels that we will be seeing in the upcoming slides, and also the reduced order modeling using Ansys Twin Builder. So we'll be now seeing the overall capabilities. So this is specifically for the Icepack Classic. So here we will get the fluid flow, both laminar flow is included and the turbulent flow. In turbulent flow, there are various turbulence model there available. Depending upon the application, you can select the most appropriate turbulent model. Then coming towards the heat transfer. So what are the heat transfer you will be getting is conduction, convection, radiation, and Joule heating. And apart from that, conjugate heat transfer. So when there is a heat transfer between a solid and a fluid phase, solid, fluid, 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 solid, and solid, fluid. At that point of time, CST comes into the picture. So that is also available. This basically known as conjugate heat transfer. Conduction is available, convection, natural convection, as well as forced convection, radiation,
ठंडे रखने हैं
radiation as well. In
और देखो
radiation,
तो
you will
देना
be
कोई
getting thermal and as well as solar. And apart from that, Joule heating is also available. Let's say you are having some few passive components connected or interconnected components are there. How the heat transfer is taking place to the near about components. For that, Joule heating is also available. Apart from that, you will be able to perform the simulation in two stages, that is steady state analysis and transient thermal analysis. Depending upon the requirement, you can either go with steady state, which is independent of time, and transient, which is dependent of time. You get the option of single phase as well as multiple phase. Species transport model is also available, in which you can create your mixture template. So when it comes to species transport, let's say you're having a cooling channel in your electronic component, and the coolant which is flowing inside is, let's say for example, it is a two fluid combination of two fluids. For example, we'll take it's glycol, and let's say 50% glycol, 50% water, or there might be any other fluid. But when it comes to more than two fluids or combination of two fluids, it is suggested to go with the species transport model. In that model, we will create two different we will add two materials, and we will give the quantity and define it like we want to give it for 50% glycol, and other rest 50% will be water. And this is how we can use a species transport model. Then it is reduced order modeling. So reduced order modeling is based on 1D. So when you are going with any CFD simulation, it will consume a time, so certain time. But if you want to reduce that time, at that period of time, Roam will help you out. And lastly, the multi-physics coupling is available. So you can couple your fluid data with mechanical Icepack, with electronics. And as per the requirement, you can couple the two different physics in through Ansys Workbench. So this is the major focus on electronics cooling, which Icepack offer across all the scales of electronic cooling components, which is starting from the chip and die to IC package, board assembly, backplane assembly, system level, and the data center, or let's say server room or open environment. These are these are the various domain you can implement this tool, and this will help you out to perform the simulation and compare it with your actual data with reduced time. So when we talk about the ice pack has primitive objects. So on the left hand side, you can see there are number of objects available. So here, if you see, there are assemblies, network, heat exchanger, openings, periodic, grills, sources, PCB, enclosure, plates, walls, blocks, fans, blowers, volumes, heat sinks, etc. So models can be rapidly created by combining these primitives. You can either drag and drop these primitives, or you can give your values x, y, and z coordinates, and you can draw these primitives. Either you can Otherwise, you have the option of MCAD and ECAD. When it comes to MCAD, you can, if you are already having a 3D object, so you can take that object to Ansys Space Clam, and then from there you can convert it to iSpec compatible geometry, and then you can import it over iSpec. Otherwise, you also have the option to create the geometry in iSpec itself. So all the major parts, components which are used in electronics are already available. You can see whether it's heat exchanger opening is there, grills is there, PCBs, enclosures. Even the fans are readily available. You just have to drag and drop. So this is some added advantage in iSpec, which is not available in Fluent. So this is the MCAD and ECAD support. So whether it is any of the electronic components, you can get that data and you can transfer it to iSpec. And for MCAD and ECAD, you will see here in Workbench, you are having one option geometry in this. This is the space claim geometry. And when you perform and convert the MCAD data to your iSpec compatible data, you can set up directly link this to iSpec setup, and you can go with the run, and you can set up your data and inputs, and then you can go with the solution. In similar manner, you can also import the trace data. When we say trace data, all your traces which are present on the board, whether it's of copper or some other material, you can include that trace, and you can also see how your heat is, what is your thermal behavior throughout your traces. So that can also be observed using iSpec. So this is transfer of classic iSpec project to AEDT. So how you can also transfer the iSpec models to AEDT or AEDT to iSpec classic projects. So when you are saving your project here, it's the option called iSpec classic project. So this is how you can go with the classic project into, you can import it into the AEDT iSpec model. So major advantage of iSpec is it takes really less time to perform the meshing for complex shapes, and highly accurate meshing, body fitted meshing is available for complex face, and concurrent meshing option for assemblies for faster meshing time. When you go with the similar meshing in space claim, in Fluent meshing or Ansys meshing, it will definitely take more time as compared to iSpec, and it will also depend on the geometry, and it will also increase the node counts. But whereas in iSpec, you have a better control of meshing, and reduced meshing time also helps to perform multiple iteration. So as you can see, these are few of the examples. This is the non-conformal mesh. Whether in this non-conformal mesh, the outer mesh and your inner mesh won't be connected. Two objects will have different meshes. But when it comes to the conformal mesh, the full assembly will be connected through mesh. Each and every component will be connected with each other. So there won't be any two different meshes or two different components. It will act as a single body and single component. When it comes to the radial heatsink, here you can see, so this is the multi-level option which resolves the fin gaps. So here your mesh count will tend to be higher as compared to other, but it will also give you a finer mesh to resolve the gaps between the fins. So here you can see the gaps are uh, larger as compared to the fins. You can see how fine the mesh is near the fins, where the fins are very pretty much finer mesh is being generated. Same as goes with the MRF1 model. It will capture the HD curve fan blade geometry. So here also you can see wherever the fan is, the mesh is s- fine, and at the rest of the side you can see the mesh is a little bit coarser. So in the similar manner, the system will automatically take the coarse and finer mesh depending upon the geometry. So basically this is the Icepack solver. So solver is basically based on Ansys Fluent. So Ansys Fluent is nothing but Ansys CFD solver, which works on finite volume method. So these are one of the methods, numerical methods. One is finite volume method, one is finite element method. So the structural analysis is done on based on the finite element method, FEM, and CFD simulation, whether it's Icepack or whether it's actual Fluent tool, that will be based on CFD. So CFD tool is always based on finite volume method in ANSYS. There is also a combination of FEM plus FEM, that is ANSYS CFX. That is basically the CFD solver, other CFD solver which is available for turbo machinery parts. So this is how your Icepack window will look like when you go with the to perform any of the run simulation. So now coming towards the third part, that is post processing. So what do you understand by post processing? Let's say we have performed the simulation, but how do we analyze or how do we see whether our component is getting heated up, whether it's getting heated up, where, what is the location, what is the temperature? So for that, we can see on the cut plane. See here, you can see the red color will indicate the higher and where the your temperature will be rise. On the right hand side you can also see there is a legend, contour legend. So here you can compare the temperature. So here all the temperature ranges are written. So this ideally at the bottom it will be the minimum range, and at the top it will be the maximum range. So when the you can compare like what is your temperature, you can get an overview overall idea, and then you can also go with the probe selection. You can pinpoint the location and see what is the exact temperature at that particular location. In similar way, if you are going to perform any simulation for fan, let's say you have performed, you have set up the things, but how do we analyze whether the fan is moving in the perfect right direction or not? Let's say we don't know, we have given the values, and our target is our fan will be rotating in clockwise direction, and we have given the RPM, but we don't know whether this RPM is will be in clockwise or anti-clockwise. Let's assume we are not aware. So let's say initially we have taken the RPM as 950 degrees. So when we proceed with the simulation in this case, how your geometry is created in which coordinates, that will also play an important role. So if your geometries are created in the negative coordinates, so your 950 will act as a negative anti-clockwise. So you have given the positive value, but your fan will rotate in the anti-clockwise direction. Our aim was to see whether the fan is rotate. It should rotate in the clockwise direction. So how we can virtually see it whether it's rotating in clockwise direction or anti-clockwise direction, and how our flow is coming out of the fan. Whether are there any recirculation areas present over there or not? So these all things we need to analyze. So these all we can analyze through post processing. So let's see here on the left hand side, there is a fan available. So here we can see the contours are plotted, and it's showing the air is coming out in the air is going inside the fan in this manner. From here, the air is going inside and it's circulating in this manner clockwise. So this is how vectors will help you out how your flow is taking place, whether it's in the corners your flow is recirculating or not. So these are few types of post processing. Now coming towards the if you see the photo behind here, the drone is there. So this is the animation of the velocity vectors around the drone model. How your velocity is behaving on the surface when your drone is lifting up. So this is how the air will behave and how your circulation and recirculation of uh, on near about zones will take up places. So these are these are the some few examples of post processing. In the similar manner, in the right hand side, you can see this is the post processing of the data center. So basically, this is also the speed post processing is there for flow inlet flow. So now coming towards the additional options which are available for the model building. So this is how your library looks like. Your library is there, in which main library is there, in which materials are included. Now you can see which material is present, whether it is fluid, solid, blowers are there. So this will all be present in your library. And you can also merge two different projects if you are working simultaneously or it's same kind and you want to merge the projects. You can also merge them using the merge option or merge project which is available in file. So there are four broadly there is an option known as macros. So macros is nothing but functionalities of Ansys Icepack offers, Icepack offers, and additional capabilities via specialized subroutines. So macros is broadly classified into the four parts known as geometry, modeling, post processing, and productivity. So when it comes to the macros, you will have the tool over here, and you can see the macros over here. Just behind in macros, you can see geometry, modeling, post processing, and productivity. When you will open each of the components separately, let's say you have opened the modeling, so heat sink wind tunnel is available, IC package is there, ice pack, cooling, coupling is there, thermoelectric cooler is there. So these are the different types of capabilities which are already present in ice pack under macros. So these are few of the advanced modeling options. So when it comes towards the multiple fluid, let's say multi-phase flows is there, or cold plates or heat exchangers, or you can see here the cold plate with glycol is there. So there are more than two fluids, and here cross flow is there. So air is cross flowing from this direction. So these are the different uh, kinds of physics which are already given you the brief. Apart from that, see, this is the for the radiation model. So direct and diffuse solar radiation applied on the antenna. This is on the antenna tower. And advanced turbulence model is also present. So if you want to see, this is the on the right hand side down. There is a transient smoke distribution from fire in a multi-floor structure. So basically, in this kind of complex simulation, you will go with the species transport model. And what this simulation is done for and how it's exactly performed is, let's say you are in a multi-level car parking, and if the fire takes up place in any of the story, how your smoke and fire will propagate, how your smoke will fill up the ceiling, and up till which level your smoke will travel until the fire is not stopped. So this kind of simulation, you can see what is the area coverage area of smoke, how dense the smoke will go up, and after what time it will come to the uh, half of the ceiling height. Let's say your ceiling height is 10 meters. So how much time it will take to fill up to 5 meters or 7 meters? Basically the visibility. So these kind of complex analysis can also be done with the help of iSpec Classic. So this type of simulation can be done through species transport modeling, where we will be defining how the location of the fire and fire, how the fire is taking up place, whether the fire is combusted, how much combustion is taking up place. This all can be done through species transport modeling. Then this example shows the multiple reference frame that is in short known as MRF modeling. MRF stands for multiple reference frame. This is for the fan modeling. So we can either extract the CAD geometry of fan blades and specify the rotational velocity, either or else we can what we can do is we can take up the primitives of fan that will be in 2D. So we can take that and we can use in our model. Else we can use this model from our CAD space claim imported model, and we have to specify the RPM. So this is the accurate thermal conductivity for packages and PCBs. So this is the detailed thermal conductivity maps examples. So this is how you can go ahead with the trace data and the metal fraction computed from the traces. So this is how your temperature thermal and performance will look like when you go with all the traces and everything through your ECAD import. So this is how your legend looks like. It indicates the lowest temperature is 0.35 and the maximum temperature is up to 387.6 degrees. So this is how you can have a little bit of comparison. And then again, you have the option for the probe and see what is the exact temperature at that particular location. So coming towards the Joule heating. So when we talk about the Joule heating, iSpec is capable of solving the DC current conduction as the part of conjugate heat transfer, which is not available in Ansys Fluent but is available in iSpec Classic. Which is available in Icepack Classic. This is one of the example. Here on the left hand side, you can see how your current is flowing up, and here is the contour of electric current density, and what which is the location where you can see the highest current flowing is this location. So in similar manner, you can also plot the contours of electrical potentials on high trace in PCB. So this the second graph or second contour shows you the electric potential contours, and the third and this is for the Joule heating, and this the last one is for the temperature distribution, how the temperature is distributed over that particular region. So this is few of the Delphi packages characterization which is available. So this is for the temperature contours on a micro lead frame plastic package with the help of natural convection chamber. So this is it's the how we have defined it. This is the top surface, the top outer surface, bottom outer surface, and this is the Delphi network final Delphi network model which has been used. This is for the kind of ROM model, which is used to reduce the time of performing the simulation. So you will get the almost near about the same results if you go with the CFD or with the ROM. But when you go with the ROM, your speed will be 26x speed up as compared to the full CFD simulation. So this is for the ISPEC and CFD process. So first of all, these are the few steps which will these are the few steps uh, these are the few steps how we will perform. So first is the geometry performance, the second is the physics, third is the mesh creation, fourth is the solution. Hello. Fifth is the post processing, and sixth is the final overview report and the summary reports, where you whatever steps you have performed, you will how whichever graphs and contours you have plotted, the system you have to click it, and the system will give you the report of the overall report. So report generation is also available in terms of HTML reports. So this is the multi-physics workflow with IcePad. So when it comes to Icepack, you can couple it with electromagnetics, whether it's chip level, Red Hawk is available, whether it's for PCB level, SI wave is available. If it's mechanical structural is available, electronics reliability, Sherlock tool is available for room, Twin Builder is available. And for electromagnetic, HFSS is there for SI waves, EMI, EMC is there. And then if we talk about the motors part, Maxwell and Q3D is also there. So this can be coupled with these many tools. iSpec can be coupled. So basically this is for the Red Hawk iSpec, which is based for the chip level thermal model. Then SI wave is there. This is for the current densities in the SI wave. So now what I will do is I will take you to the tool and I will showcase you one of the models. So this is one of the models which I am already having it. So I will show you. I'll zoom it. Here there are two fans. Here over there is one heat sink. So four ramps are there. These are the grills. So on the left hand side, you can see this is your project and this is your library. So in the project, you will see we need to follow this step one by one so that it will be we don't miss out any of the steps. So first step is the problem setup. In that basic parameters is there, local codes are there, then solution settings is there, groups post processing. And here in the model you will see material is here material is there. And when we see the cabinet, so this is our overall cabinet and what are the things included in the cabinet is defined over here. So this is the side max and on the bottom you can see this here we can change the name selection. This is the plane where the cabinet has been located and this is the start and end points in the X, Y and Z coordinates. So this is first is x-axis, the starting point is 0.175 meter in the x coordinate and ye is endpoint. So this is how the different sides are there. The left fan is available. So when you are having a fan, you can see from select from here whether your geometry is circular, rectangular. By mistake, selected. So circular geometry is there. So these are the x, y, and z coordinates in radius, and this is the plane where the your coordinates on which plane your fan is presented. In similar way, left fan is their board. This is the board. If you can see the highlighted part, this is the board. This is the large flash. This is the large flash. This one is the small flash. And these are the four RAMs. If I zoom it here over here, you can see this is the DDR. This is DDR1, DDR2, DDR3, DDR4, and then there is this bridge is there. This is the bridge, and then we have the AGP, and there is the heat sink. The above one is the heat sink. So these are all the coordinates of the system, and these are all the available primitives on the left hand side. Small strip is there. These are all the available primitives. So when we go with the any of the simulation, so first of all we will import it, or let's say I have imported this primitives, and I now want to set up the basic thermal problem. I'll I need to give the fans, define how much rotation RPM the fan is taking or whatever the flow rate is. So these all things I will showcase you how we can perform it. So let's say this is the problem setup. When you double click on it, it will say choose the variables, solve your velocities and the temperature. You can go with the next flow as inlet outlet, force convection is there. Yes, we have with the force convection. Set the flow regime to turbulent. Yes, we are opting for the turbulent solution. And this is here the turbulence, various kind of turbulence model which is available. For now, we will be considering zero equation. If your model is complex, you can go with the two equation K epsilon, or you can go with SK omega SST, which is the last model. Or if you are going with the single equation, your product requires not that much complex turbulence, then we can go with the Sparta-Salmaras method. RNGK epsilon is available and hence two equation model is available. So we will choose our equations as per the requirement. And then we will see include the heat transfer due to radiation. Ignore if you want to ignore you're not considered for the radiation. You can just ignore it. Else you can include it. How you want to include the radiation surface to surface model is there, discrete order model is there, or you want to use the solar ray tracing. And when we go with that option, we can include the solar radiation. Then we'll set up the variables, whether it is steady state or we want to go with the transient analysis, adjust based on the adjust properties based on altitude. So if your let's say component is placed on some altitude, you can always define it over here. So this is how we will go and done. I've already set up this case, so the done option is not showing up over here. Now coming towards the basic parameters. So when we come with the basic parameters, here is the general setup, default, transient, and advanced setup is there. When we go with the general setup, we want to see variables to be solved, whether it is flow and temperature both, or either you want to just see the velocity and pressure, and you are not considered for temperature. So you can select it accordingly. Flow regime turbulent, in turbulent which equation. So this is how you can select it from here also. Then we will define the ambient condition, radiation temperature will be defining it as a temperature 20 degrees, the ambient temperature. These are all the ambient condition. And we will be defining the fluid, default solid, default surfaces. Then the transient setup. If you are going with the transient, you need to provide the start time and the end time. We'll select over here the steady as we are not going to run the simulation for the transient part, and there are some few advanced settings. So here you can define your if you are going with ideal gas flow, or you're going with Bosonicky law or operating conditions, we can add it over here. So this is how we can set up our basic uh, problem. Then coming towards the materials and all the things, we can select this directly. Select, let's say I want to see for the fan. So let's say I double click it, double click on fan. You can go to the geometry. It will show you, it will give you the radius, the properties, fan type is intake or exhaust fan or internal fan. You can define it over here. You can give the CFM value over here, whether, or you can go with the mass flow rate. So here we have given the value of 5 CFM. So these are a few of the properties which we can define. You can also give the flow type, whether it is linear or non-linear or it's fixed. Total temperature and gauge pressure also, if you want to specify it, but depending upon the application, you can depend. You can specify it over here, and then just you have to click update. In similar manner, we will see for the heat sink. So heatsink geometry is there. Whenever you select any of the geometry, it will highlight it over here. So I have selected the heatsink geometry. In the properties, the simplified fin type is the longitudinal fin type. Here the fin setup is there. The thickness of the fin is there. Spacing between the fins is there. Flow and thermal data is there. Constant. We have taken it as for now for the constant. Pressure loss, the type of loss is loss coefficient, and the interference, if is any of the interference is there. So we can give the properties of the different components by double clicking on it. We can give the properties. Now we will see the meshing part. So let's say on the top, this ribbon, you can see there is a cuboid box known as generate mesh. You can see small grids are there. So you just have to click over here and you just have to generate the mesh. So let's say when you generate the mesh here, the measure type is measure HD. You can use hex unstructure or hex Cartesian. We will go with mesh HD, and then we can just click on generate the mesh. So once you click, your meshing has been generating, and you can see done loading the mesh over here. So when you go with the mesh, you will see the minimum element size over here and the minimum gap between the two elements over here. And when you go to the local over here, you can see, yeah, in multi-level you will get the option. When the your object is compatible with the multi-level option, you can allow multi-level and you can perform the multi-level mesh. So these are the global parameters. So minimum gap, minimum element gap is defined, minimum elements on edges defined, and maximum size ratios is defined. Once we generate the mesh, we can now go to display from settings. So first option is settings, then we can go to display and we can display the mesh, and we can select volume. So as my heatsink was already selected, so we can, you can see the mesh has been generated over the heatsink, and this is how your mesh will be looking like, will look like. You can also change the mesh color. So if you want to see that on the cut plane how your mesh is done, or you want to see your volume and surface all together. So the yellow part indicates the surface mesh, the white one is the volume mesh, and the black one is the cut plane mesh, gray color. So this is on the cut plane. You can see this is at exactly at the center. It is on the cut plane. So from for volume, we can select from over here. So once we have done this meshing part, let's say we want to see the mesh on the different location. So from here we can select, let's say large flash. I want to see how my mesh is. So I will select large flash over here. I will go to display and I will go to volume. So you can see here the volume mesh has been displayed for the large mesh. Similar way, if I want to see the surface mesh. So this is the surface mesh for that particular region. So once the meshing has been done, you can close this and you can go to solve option over here. So when we go to solve, there is a option known as run solution. Here your setup is already, I have defined the setup, I have given the time steps and auto save the interval is for the 100 iterations. I will just start the solution. A solution already exists, overwrite it, yes. I want to override the previous solution and now the this window will come up. See, all their files will be getting written over here. And once your solution starts, it will showcase the continuity, momentum, and XYZ equations in the graphical manner that will also come up at the end. See here. These are the number of iterations which are going to be performed, which are going, and the different color indicates X, Y, Z continuity. So the continuity and the momentum equation, which are the basically used for any of the CFD tool. So once this is done, I will just simply click on done and I want to see the post processing. So for post processing, you can always see here the pictorial colorful parts are present. So object face is there. So here I can obviously go and I can select whichever object. So let's see, I am focused how my temperature is behaving on the heat sink. So I will select the heat sink, then I will give accept over here. I want to also see the mesh and contours. So these are the parameters which I have selected and I will then give a display. So once I give the display, it will showcase me which is my maximum location and which is my minimum location. You can also access the same from the left hand side post processing. Let's say I don't want to see the mesh. I have only considered in the this region. So here how you can see, and this is the your legend from where you can compare the maximum temperature rise is of 87.9 and the minimum is 20 degrees. So this is how you can get a comparison. So this is the point. For the point, we can select the position over here and then we can see over the temperature for that particular point. So now let's see, I want to post process another face or I want to see it on the cut plane and I'll see the direction through Z. Okay, update and display. So for animations, you can go with here. When you go with the transient, we can also go with this animation. So we can see how the animation is taking up place. And let's see, we want to see for how the velocities and things are behaving when we go with the fan, left fan, except like show vectors and display. So this is how it will show you how your air is coming up in from which direction, whether it is coming inside the domain or getting out from the domain. So we have defined this as an intake fan. So it's taking as the air will be coming inside the domain. So this is how the demo and the workflow of Ansys Icepack is.
Good afternoon and good evening to everyone. Myself, Deepesh, and I am basically working as a technical specialist for high frequency solutions in Ansys, in ARK solutions. And I'll couple of minutes in coming couple of minutes, I will explain some of the key challenges in electronics as well as in the PCB analysis. specifically in PCB side when it comes to the using the Ansys electronics tools. So basically, Ansys electronic tools will be called also the graphical user interface is basically called is Ansys electronic desktop, which has one GUI, and it will work with the different applications, whether it's a PCB analysis or whether it's a thermal analysis. So I'll quickly go through the electronics intro, key product overview, and electronics reliability, SI wave, HFSS 3D layout, and some of the workflows which we use for doing the PCB analysis, whether it's a signal integrity, whether it's integrity, whether it's the EMC solution, or whether it's a, I think thermal already, I think it's explained by Shubham. So I'm just skipping the thermal reliability part, but remaining three part I will cover in this session. So meanwhile, if you have any query, please write in the chat box. We will try to answer in the later part of our session, or you can ask in the later part of the presentation. Yeah. So we have different product and a collection of products in our portfolio in Ansys. When it comes to the very high frequency, when I say high frequency, that means I'm talking about the mostly inside of the antennas, RF, microwave, and even the PCBs also. Why? Because the PCBs are operating. Uh, Specifically, I'm not talking about the bareboard PCB. Actually, the PCB is a supporting medium. The PCB has the different components and different controllers which are operating at a very high speed, okay, at a very high frequency. So that kind of analysis also comes into the these kinds of simulation tools, okay, like packages, IC sections, where we have to do the analysis in terms of signal and power. We can do it in a HFSS. So HFSS is a gold standard tool for the high frequency, high speed design. It is based, it has different solvers. So what is solvers? Solvers are nothing but a computational mathematical tools, which is actually running in the background to solve the geometry. Okay. And those are solving the geometry with the help of a mesh. And those meshes are at a unit level, the Maxwell equations. Okay. So it has different solvers like FEM, IE. Those are full wave solvers. We have also asymptotic, which is a shooting and bouncing ray, kind of light rays traveling and reflecting back from the any metallic or different kind of surfaces. So that kind of analysis is also possible. And not even these are the solvers are there. We can also integrate these solvers to solve some of the complex problems of the RF environment. Okay, and that approach is basically called as the hybrid approach. Okay, that is also possible. Now, next comes to the SI wave. SI wave is dedicated for the PCB. When it comes to the PCB analysis, SI wave is quite useful tool. Okay, it is actually not a completely 3D. It's a kind of 2.5D. Okay, and it uses the full wave solvers to solve the PCBs and the components which are placed on the bare PCB. Okay, so it is specialized tool for the signal power and EMI EMC for the board level analysis. We can do it quite easily in the SI wave. Okay, sorry. Hello. Hello. Hello.
Deepesh, sir, you continue. I have muted.
Dipesh, you're audible.
You
And you
continue,
can
sir.
continue. You can continue.
Yeah. Okay. Okay. So actually, I was getting some background noise, so I thought like, okay, no problem. So
So
Icepack, I think all, yeah, yeah. Icepack is basically a tool which is used for the electronics thermal management (ETM). I think already it is described by Shubham, so I'm just skipping it. Q3D is a tool which is basically used for the parasitic extractions. So when I say parasitic extractions, means When we are talking about frequency terms, high frequency or either low frequencies, we have some certain some parameters which which is basically impacting our designs. Okay, just like resistance, inductance, capacitance, and conductance, R and CG. So all those are very much important, and for extracting those parameters, we use this tool Q3D extractor. So where the application will be, it can be used as a PCB where we want to extract the inductance and the capacitance. It can be used as a bus bar parasitic extraction like resistance or at a particular frequency or capacitance at a particular frequency in a cable. So it's a kind of you can say like it's a supporting tool for HFSS and SI wave. If you want to more deep dive into the analysis, you can use the Q3D tool. Okay. So now EMA 3D cable. Yeah, this next tool is basically used for the cable analysis, specifically for the cable. Okay, it has a certain workflow for the cable EMI/EMC, like the routing of the cable and all those things. We can use the EMA 3D cable product. EMA 3D charge is focused for charging and discharging phenomena. Basically, it is used in the aerospace industries where arcing and some kind of semiconductor industries where discharge will be quite important. There, this tool is very helpful in these cases. So this is also one tool where electronics product can be utilized. Now, next is New Hertz filter. New Hertz filter is dedicated for RF filter design and analysis. So it's a template-based tool. You can hello. Can you mute Vishal to everyone? I think I'm getting some noise. Okay, thank you. So this New Hertz filter solutions basically dedicated for the RF filters, where we can based on some certain parameters, we can design it in New Hertz and then we can export in HFSS and we can optimize it in HFSS also. Okay. So Ansys Electronics, there is a quite significant challenges in these areas like electrifications, EMI, EMC, RFIC, 5Gs, 6Gs, reliability in terms of automotive, aerospace, uh, and other consumer electronics industry. So these are the products which can be quite helpful when you do these kinds of analysis at a very high speed and high data rate. So core for core product like HFSS dedicated for high speed interconnect filters ICs, which I have already shown you. And next is the SI wave that is dedicated for the PCB IC package EMI EMC high speed channels. We can analyze it with the data rates and with eye opening and eye closing analysis quite easily. Next is Icepack. I think Icepack is already been described by Shubham, so I will just skip it. Okay. So next is the Maxwell. Maxwell is a low frequency part where EM analysis is performed at a low frequency. Okay, like motors, actuators, and magnetic sensors, and different kind of electromechanical designs. There the Maxwell is used. Yeah. Any question is there? Okay. Please mute yourself. If you have any question, you can put in the chat box, or either you can ask in the later part of our session. That would be very helpful for us to go this session smoother. Okay, now comes to the electronics reliability. So in the electronics reliability, as I mentioned, there are many applications when it comes to the electronics will come. Why? Because electronics is a part of nowadays in each and every industry. Okay, so what is the benefit here? You can increase number of features, lowering the bill of material cost and head counts. You can minimize it. You can accelerate time to market, improving first pass yield, decreasing the warranty rates, and electronics is critical to all electronic trends, specifically in a consumer and automotive side as well. So some of the things, one example is shown here. This is for the PCB, signal and power integrity analysis. Like, yeah. So you might ask one question: why signal and power integrity? Because signal and power integrities are basically one of the first steps to optimize your uh, uh, design in terms of electronics, PCBs, and the PCB with the components. But if you are not improving your design at a signal and power level, definitely it is going to reflect into your EMI and EMC problems. Okay. So where what is the process in that way? I will explain it in the later part of the examples. Uh, you can perform overall PCBs, signal performance, cable performance, traces performance in terms of the as a channel with a high data rate and high speed. Okay, I'm talking about high speed. That means I'm talking about digital signals. Okay, and you can check the emissions. You can use the shielding effectiveness to suppress outside to going this emission outside your domain. I mean, from the chassis or any um, uh, supporting medium is there. We can use this simulation analysis quite effectively. I hope you are also aware about these four pillars. Thermal, I think already it has been discussed, so I'm not going to discuss. Signal integrity is basically ensuring whatever from the transmitter one, that is digital one, it should be received as a digital one at a receiver. But if it is changing, then there is a problem in the channel. So the channel analysis need to be done. So that kind of analysis is basically called as a signal analysis. So, and when it comes to the power analysis, basically, so a power analysis basically ensures all the components will which are placed on the board gets a proper power that is within the limit. Okay, it should not, if like if one component is designed at a 5 volt and it is getting at a 10 volt, obviously that is going to be burned. Thermal integrity, I think already Subham is discussed already. Next is EMI EMC, basically for compatibility and interference. Interference means the source should not generate a very large amount of interference. And at a similar time, our device should be more compatible with these emissions which is coming from the source side. Means a victim should be strong enough and emissions should be less. Okay? So those kinds of things, whatever you do in a physical way, we same thing we'll do here in a simulation way. But the information which you are using it in a physical site, that we have to provide it into the simulation properly and in a correct way. And if you face any challenge, we are here to help you in that way, like how you have to provide it those information. So I think already I have described it, signal integrity. So one of the thing is like the eye diagram. Eye diagram is basically used to analyze the channel. Okay, so if I have sent a signal from transmitter to receiver, okay, so that means a signal's eye is open. But at a receiver, if this eye opened eye becomes closed, that means we see eye is closed and signal is lost. So our aim is to maintain this eye open. Okay. So that's why we do the simulation. What are the things we have to do in a channel wise? There are various factors like crosstalk, jitter, impedance mismatch. Those all things need to be analyzed, and that can be analyzed through the simulation in SI wave. Okay, so this is what actually shown here. You see here at a signal, transmitter side I is open, signal is one. This is the channel, and channel means routing and the VS will be all will be there. So when the signal is transmitted from um, source to receiver side, transmitted to receiver, this is going to be completely lost. So our signal is completely overlapping. That means channel is completely discontinuities in the past because of discontinuity, impedance mismatch, crosstalk, jitter, all those factors will be there. Those all can be analyzed in SIV. Okay, at a very high speed, if you see those kinds of analysis is also possible. That is basically called as a DDR double data rate analysis, and this is quite important. And there is a pass-fail criteria for JEDC standard, which allows um, which allows to analyze a high-speed channel. So that kind of analysis we can perform in SI wave. Okay, so SI wave has a complete DDR latest version. You can analyze DDR6 and DDR6 plus also is coming in the newer versions. So you can generate a report, JDC sign off report, which is basically having valid timing, jitter, self delay, slew rate, data valid window, noise, all those things you can generate in a single go result. Only you need to bring the PCB with your components with your DDR, and you need to define the channel, and then you can analyze it with a time domain analysis. You can also see the frequency domain as well. Okay, so next is a power integrity. So power integrity is something which is quite important when it comes to the delivering power to the components on a PCB board. So whether it's a IC, whether it's a BGT, whether it's a MOSFET, or whether it's a resistor, whether it's an inductor, all requires power to operate. Okay, so the source is coming from obviously from battery or voltage regulator or any other IC. Okay, so this analysis importance also increases. Why? Because if the power is switching or power having fluctuation, okay, like sometimes it's a 5 volt or sometimes it's 5.5, 4.5. Obviously, that is going to hamper our um, device performance. Okay, so that we don't want. So for those kinds of analysis, we have a complete power integrity analysis like DC power delivery, PDN, PI advisor, okay, with the capacitor optimization technique, so that we can minimize these fluctuation on the component size, component level as well. Okay, and the impact of this power variation also having in a current and voltage, you will get lesser effect of the EMI EMC. If you are not analyzing it, obviously that is going to impact in your EMI EMC problems. I think that is explained here in that one, like power integrity challenges, which I have already explained. So I'm skipping it, going to EMI EMC. So EMC or two things are there: electromagnetics compatibility and electromagnetics interference. So interference means what? It is a like two devices are operating nearby. Obviously, one device will generate some signal and other device will receive some signal. Okay, so the device which is generating a signal, which is producing an interference, we call it as a source, and the device which is receiving, the second device which is receiving the signal that we call it is as a victim. So what is our intention? There is a compliances are made for those. Like our aim is to reduce the emission, okay, at EMI, like from source side, electromagnetic interference, and at the same time, the compatibility should be more. Okay, so if the device is compatible enough, we can say, okay, this is passing in the EMC test with these compliances. So that kind of importance is very much important because nowadays, as I told in the beginning of the presentation, electronics presence is widely nowadays. And you can see there are a lot of devices, electronic devices are present in a very small area. Okay. Even if you talk about automotive sector, okay. In automotive sectors, earlier days, only one MCUs is there or ECUs are there. Nowadays, 10 or 20 or maybe a very large number of amounts are there. So obviously, those controlling, those functioning requires a lot of hardware in terms of electronics. So if a design is not properly done, obviously you will face the challenge in the either signal power, and the signal power will lead those challenges into emissions. Okay, emissions means electromagnetic emissions or compatibility problems. So this is one of the conducted emission test, which has been done in Ansys HFSS. So what is basically been achieved here? With the help of HFSS, we can use the simulation to get the extract the parasitics of the cable. Here the cables are there. Let me show you the pointer. Cable connectors, PCBs, and LISN and the load. So all those parasitics are extracted, and later it is been connected according to the schematic or according to the functionality of the circuit or system, and done with the transient analysis, which we have already available in Nexim circuit, where we can do the Nexim transient analysis, and we'll get the time domain behavior will be captured of that particular system completely, this environment. And this time domain behavior we can utilize in the converting into the frequency domain with the help of FFT algorithm, which is available in the Ansys Nexim circuit tool itself. Okay. And then we can see the frequency behavior, whether it's a conducted, whether it's a radiated, both. So conducted kind of emission is available on the cables, which is going to the power. And this is basically it's a kind of radiated kind of emissions. It is not in the form of conduction. It is kind of form of radiation, which is coming from the EUT to antenna, and then it will be captured how much the power is basically observed on particular distance from the EUT. Based on the compliances, it may vary. This limit may vary. So some kind one case study is being shown for GEMCO. Here you can see conduct radiated emission is done for a PCB for 3 meter distance, and you can see also the like results are quite comparable with these simulations. Now SI wave is a tool. I think already I have given the one information, but still I'll explain it. Dedicated for the PCB. Okay. So it has a capability to analyze signal, power, EMI, EMC for a high speed designs. Okay, high speed that means which having the microcontroller or the a very high data rate switching is happening between the one component to another component. Means one IC to another IC or one circuit to another circuit which is available on the board. So extraction capability of the SI wave. What are the tools can be utilized here? Can be design tools can be utilized. Basically, the design SI wave is not a designing tool; it is a tool for the analysis. First of all, we need to understand we can bring it different design PCB designs, ECAD formats like Mentor Graphics, LTM, Jukin, IPC 2581, ODB++, NCC EDB. Okay, Gerber is also there, but Gerber generally most of the time we don't recommend it because sometimes in the translation of the EDB files, data will be lost. So these formats are very popular in the market and it's very much used in these days. And these are already readily available for the different design formats. Okay, so You can bring it, you can draw, the drawing editor will be there. You can analyze with the full wave 2.5D full wave EM solvers to extract some of the parameters like DC analysis, AC analysis, resonant mode, and spice models. So what is the DC analysis? You can analyze the I square R losses, current distribution, signal flow graph, as well as thermal coupling with Icepack to see the temperature. If you want to see the temperature, you can couple with Icepack and you can see the temperature on a PCB level also. Okay, and that plot is quite significant and good. You can also see that thing as well. Now, next thing is AC analysis, AC impedance analysis, S parameter extractions, near field and far field crosstalk, as well as capacitor optimization. So this capacitor optimization will is quite important when it comes to um, minimizing the power integrity challenges. Okay, so that can be done in AC analysis. Now, resonant mode are basically used in the analysis where we wanted to see what are the areas where we are getting different frequency component on the PCB board with the different components. Okay. And the fourth one is basically SPICE models. So SPICE model like Nexim SPICE, Cadence, Spectroscopy SPICE, Maxwell SPICE, those all files can be utilized in SI wave as well. Or either you can export it from there directly to other tools. Okay. Like what is the workflow for the when you import any PCB board? You can verify the stack up. You can verify the pad stack. You can also do some changes in terms of stack up in the pad, like thickness, the electric constant, and some of the parameters. You can tweak it here as well. Verify power and ground needs. Sanitize the layout when you are bringing it. And these some different application used for the analysis purpose, like S parameter capacitor models, spice net list, DCIR analysis, which I was talking earlier, PI analysis, power integrity analysis. So these features are also available in this process of analysis. So highlighted features will be speed up the HPC, layout scan capabilities, single environment where you can automate and with the AEDT integrate to AEDT, Ansys electronic desktop to analyze the TDR wizard, time domain analysis. You can do the signal analysis. Okay, you can also do the power delivery network of the AC flow. Okay, this is completely automated approach, CPS based workflow. Chip package, basically chip package analysis is there. So it's a quite accurate and completely automated workflow. Only you have to define the where what are the nets which you are going to configure into the simulation, and then later you can do this analysis very significantly and very easily. DCI and thermal is basically we extract the power map through the analysis, and in this analysis is we capture the voltage and current of the PCB, and we can also couple with this. Sorry, we can also couple this voltage and current directly to the IcePack to see the temperature behavior. Now it comes to HFSS 3D layout. In HFSS itself, we can also do the 3D analysis of the PCB board and the component. So what is the advantage of the 3D? So there are two ways which I have already explained of doing the PCB simulations are there. One is with the SI wave. SI wave is not a full 3D solver. It's a kind of 2.5D kind of integral equations are used to solve the on a surface mesh kind of thing. But when it comes to HFSS 3D layout, that is solving the PCB in a 3D environment, creating the mesh in a 3D environment. Okay, so it's one PCB you can also use for HFSS 3D layout or SI wave. Okay, you can also compare the results as well. Um, the thing is, like, if you want more precise and more detailed analysis, you can go to the HFSS 3D also. Okay, but some of the process has um, process-wise, HFSS 3D is bit you have to invest some time there. SI Wave is quite easily you can give those information like self setup and all these things. Um, but HFSS 3D requires some of the prior HFSS information. Then you can use this HFSS 3D tool. I'm not saying that HFSS 3D is quite improved tool as compared to SI Wave. No, and this is both the same approach is there. You will get one is solving into 2.5D and one is solving in 3D. So obviously, 3D has more capturing information as compared to 2.5D. Okay. These are some of the products which are shown here. HFSS, Q3D circuit, Icepack, Maxwell, Simpler, and these are some of the top ribbons shown here. Mostly, the purpose of showing is like different solvers and different techniques. Based on our application, we can utilize it, these data as well. So in 3D, HFSS 3D layout, uh, we can design in a 3D environments the components, or either we can convert in a 3D components. So complete PCB can be also brought. Okay, and some of the advantage like you can encrypt some of the components which you don't want to share with your vendors, and those components are only decrypted when the proper passwords are provided uh, to solve those geometries. Okay. Okay. So SI workflow analysis. What is the workflow? So in that, first we extract the S parameter, build the circuit. Okay, and basically what we are doing here, we with the channel we put some port. Port means we are configuring with RLGC parameters. Okay, extracting the parasitics, connecting it into the circuit, doing the transient simulation response, and then we can see and analyze the results in terms of the very high speed channels. You can see the digital high data rates are there, and also we can see the I analysis, which is quite significant in these kinds of analysis. We can put I data analysis at a transmitter, at a receiver, and we can see how much the data loss is happening in terms of I open or I close. That we can see. Now, the power integrity analysis when it comes to the board. Obviously, peak voltage is quite damaging to the supply to circuits which are available on the PCB. So, in a non-configured approach, you can see that a lot of these states are there, the limits are there, like 1.8 volt plus minus 10% is shown here. So it's a violation you can see here. But the aim is to optimize enough and to control the this power value within the limit. Okay, if the limit is failing, obviously this will be damaging to the PCBs or to the system wherever it is placed, this electronic PCB. So with the help of capacitors optimization technique, which is the PI advisor, which is available in SI Wave, we can optimize this power performance with the help of impedance characterizations and with the help of imported spice model of the capacitors, and we can minimize those ripples within the limit. So this is one good example of the PI analysis where we are improving the performance of the power levels, voltage supply levels. Now, next is a PCB CERE simulation workflow. So what is the first step? We import the PCB layout, EDV format in ODV++ or IPC1. There are different formats are there. Um, spice parameter model assigned. Port creation need to be done. Port creation means we are talking about a high frequency. That means we need to take care of the impedance values. Those impedance values will be captured with the help of the port creations. Okay. So when the port creation done, SYZ parameters will be extracted. After the extraction of the SY parameter, we can import as a network block into the Nexim circuit. Okay. Import active and passive components in the SPICE model, in unencrypted SPICE model, MOSFETs and ICs. Make connection in the circuit according to the schematic. Okay, switching frequency, rise time, fall time, load configuration, all need to be done properly. Then the next step is the transient analysis. So this transient analysis is the time domain information. We can convert those information into the frequency domain with the help of FFT algorithm, which is available in the solver itself. So we can see the conducted emissions plot. If we want to see the radiated emission plots, we need to push back those data back to the solver again, and we can see the report in the we need to run the far field analysis. And after the running of the far field analysis, we can see the radiated emissions plot quite, and that is a with the different compliances we can use 3 meter, 5 meter, 10 meters based on our requirement. Yeah, that's all from my side. If you have any questions, please ask. I'll see in the chat box if any questions are there. Okay. Any questions? Please ask. If you have any questions, please ask.
Hello, sir. Anuradha this
Yeah.
side.
Yeah. Hi.
Sir, you have explained about how to simulate for emissions. Is
Mhm.
there any solution available in Ansys for this immunity also, if we can simulate for the
Yes,
OCP?
we have. What kind of immunity? Radiated or conducted? Both are there.
Both radiated and conducted
Yes.
immunity.
Yes. It is there.
Okay, so for like in radiated immunity, is there a complete range of 20 megahertz to 2 giga or 4 gigahertz? It is there.
Yeah. Yeah. Actually, I'll answer this question. The tool is not limiting you to any frequency limit. You can do for a wide range of frequencies. There is tool. Only thing is whatever the workflow I have shown you, that is for conducted and radiated emissions. For the
Yeah.
RI and the like a conducted immunity, both having the different workflow.
Okay.
Okay. So immunity side, when we are going, that means the fields and the consideration of the power, those things are quite important. Okay,
Correct.
because so those are having different compliance wise is there, like IEC or different compliances. AIS is there for detected immunity. Generally, immunity side will be considered in a quite rigorous considerations. So those things are we can also incorporate into the simulations, and we have the process also.
Okay, sir. Thank you.
If you need more information, you can reach out to us. We'll definitely help you in that.
Okay. Okay, sir.
Yeah.
Thank you.
Thank you.